Okay, so hi all. In this video, we will continue with where we left off last time, which is with hash functions and hash tables and all that other good stuff. I think this is roughly the slide, or maybe actually the slide that we left off on last time. But before we resume with that, I'll just remind you of what the idea of a hash function and a hash table and all of this stuff is meant to be. So I think an idea of storing data more efficiently, rather than using just a list, right, or an array, or any of our versions of that, is to maybe think really about the structure and how do I want to store this in a way so that hopefully I can both store and then eventually retrieve or find data the fastest way possible. So for sure, it's you can't argue, I don't think, that if there was a way for us to say, well, based on the data that I'm storing, I'm going to actually compute or assign a location for where that data belongs. This is the first time we, I think, have, for the most part, really thought about doing anything like that. In the past, it's always been, well, whatever order the data comes to us in, that's more or less the order that we stick them in wherever they go in our array or linked list or whatever. Even if we've done, you guys coded in order insertion, where we're inserting into a list, into a linked list, but we put things in the right place, in terms of numerical order. Well, that isn't assigning a location to something, though, is it? That's just assigning or that's storing data with a structure in mind or with an organizational structure in mind. But that doesn't say, oh, if I want to insert the number 63, I'm computing where it needs to be so that I could go right to it the next time. That's not what inserting an order means. But a hash table, or hashing in general, as an idea, is that, right? Is the idea of hashing is that we say, well, you're going to store some data. There's going to be a value that you're using as sort of your unique identifier. That's known as the key. And we're going to make a table, which we're getting to that today, of what exact structure this is going to take. But the idea of a table, right? Think about like an Excel spreadsheet or something is a good example of a table. It has rows and columns. What's my organizational criteria is that I'm going to say, well, based on the key value, whatever number that is, I'm going to actually compute or figure out where this data should go in this data structure. Now that's good on both ends, because when I'm storing it, I'm not just randomly saying, well, where's the next available free space? That's kind of mostly what we do when we store stuff. But this is not going to be so careless and haphazard. It's going to say, oh no, I'm going to tell you exactly where to put this. And the main benefit of that being that then when I go look for it later, I can find it immediately, or at least faster than I might otherwise. So the hash value is going to be where I store it, and the hash function is going to be my means of figuring out the hash value based on the key. All right, so we chatted a little bit about this last time. I think this is the example that we left ourselves with, which was sort of a toy example of what if in class I was trying to figure out a more clever way to store the data for the 10. I think there's actually 10 of you. I think I only had 9 yesterday when I recorded this. But the 10, right? There's 10 of you in class. So how would I store where should I store your 10 names so that I could find you or anybody more quickly? So a very rudimentary approach would be to say, well, maybe I'll organize student files by birth month. And that way, at least when I try to look someone up later, I only have to look in the row associated with their month. Which is, okay, this is a little funny, I guess, or silly, that birth month is probably not the most sophisticated thing I could use, but okay, as a first example, it's not bad. So I went through our class, and as I was roaming around, and I would have asked you in person, what month were you born in, what month you were born in, I was doing pretty good for a while, until I started to get towards the end, when I realized, I think when I went to insert Sam, that her birth month is the same as Jeff's, and Jeff was already taking up this spot, or this slot in my list here. And so we sort of have a conundrum of, oh, what am I supposed to do? I like this idea of putting you all, organizing you by birth month. Like that is kind of clever or handy. But what happens if there's 2 people with the same birth month, which obviously is likely to happen in a class even of 10? there's I won't get all mathy on you, but there's a more than 50% chance the two of you were born in the same month. So this is going to happen. So what am I supposed to do? So there's a couple of ways of dealing with what's known as a collision, and we're going to look at one option is to find the next available spot. And another option, though, which is the one we're going to mostly consider, is going to involve us creating space off to the side, quite literally what I did here, and say, oh, okay, you want this list of people organized by birth month, fine. But if you happen to have more than one person with a given birth month, don't just give up when you already have it filled. Just build a list going horizontally with as many, in this case, September people as you need. And of course, a linked list, which is what I've outlined in green here, is our friend, because our linked list lets us build these things up as we need them and delete things as we don't need them and, move stuff around, right? We have all kinds of flexibility. So how do we deal with this, right? So the fancy word for when you have more than one data item that's getting hashed or assigned to the same location, this is known as a data collision. Pretty good name. Literally, two pieces of data are colliding because they're trying to jump into the same spot. So how do we do this? So one popular way is by a process known as chaining, and I think you read about this. Data chaining or chaining. The other, when we look for the next available spot, I believe is called linear probing, maybe, or just probing. I think you read about that as well. There's not much to that, so we're not going to say a whole lot, at least in class, about that. But chaining is a little more sophisticated, so we will talk about this. So what's the idea of chaining or data chaining? So as we've said, right, the idea is that maybe then instead of having an array, like when I was envisioning this red thing earlier, it was right here. I was imagining it to just be a traditional array. I'm using a struct here, student. That's just because I have a lot of stuff to track about each of you. But this is just a regular old array with boxes, and I fill the boxes. Well, I can't really do what I depicted in green here. I can't say, oh, hey, out of this array box, start sticking these guys. I can't actually do that. So I have to maybe reconsider a little bit what my main structure is. So how about we try this? So I underlined it here. So let's, instead of having an array of students or whatever the data that you're storing, let's have an array of pointers or an array of linked lists. And then, of course, each node of my linked list can hold data. And the idea then is that an element, you're still using the hash function to decide which row, you could say which row of the table are you putting it in, but each row now is going to consist of an entire linked list, an ever-evolving linked list of nodes, which we're very familiar with at this point in the semester. So I'm still going to use the hash function to say, oh, okay, you go in slot 3 or whatever, but at slot 3, rather than there being just a single box, there's going to be there's going to be a pointer, a first pointer, and it's going to point to a whole list of nodes, all of which got hashed to location 3 because they were all born in March, right? If I'm using my birth month example again, right? So so there's maybe a downside to this, which I'll ask you to tell me about a little bit later, but structurally, this is still pretty good in that I am going to still cluster together all of the data items that have the same hash value. So when I'm, for example, going back through after the fact and I'm looking for something, I'm still going to use the hash function to say, well, which row or which slot is this thing possibly in? So while I won't have to look through the whole list, I may still have to do a little bit of searching because, of course, I will have a linked list sticking out of each of these. Okay, so let's do the usual. Here's our cute animation of this process. So first of all, I have a hash table that's depicted on the left here, going up and down. I guess I have 0 through 6. So typically, I think I mentioned this in the last video, we'll use just the mod function, which is the remainder function. And of course, if I have 7, I have 7 rows here, or 7 slots, 0 through 6. If you mod by 7, of course, that makes sense, hopefully, because the remainder is, when you mod by 7, is 0 through 6. Right? So we'll often just do something like this. I think in all our examples we will, that the list will have size, whatever n, size slots, and then I'm modding by size, or n, whatever you want to call that. Okay, So, but now each of these, it's not a coincidence that I used our little null notation for pointers. These aren't boxes to hold data. So this is the place where I think people get a little messed up sometimes, is you're like, oh, I'm going to put data here. No, you're not. You're going to make an array, which this is, look, 0 through 6, I have slots, but I'm making an array of linked lists. So what are these? These are pointers, which of course we all know that you can't store data on top of a pointer. You can store data at the end of a pointer in a new box, right? But the array itself is going to be an array of pointers, where right now, remember our little diagonal line like this means null. So right now I have an array of 7 pointers, and they're all pointed at the moment to null, which is right because there's nothing in any of these rows yet. So let's see what happens when I use chaining. So let's say I'm going to insert an object that has a key value of 31. Maybe that's some sort of an ID number or whatever. Then I'm going to use the hash function. I'm going to hash it. I'm going to hash 31. When I mod by 7, I get a remainder of 3. So it's going to say, oh, all right, you want to go in row 3 or slot 3 of this hash table. So I'm going to do that. Now I'll flash you back for a second. Right now I have a pointer there at 3, and it's pointing to null. But now I'm going to insert this new object, which has a value of 31. And I'm going to put it in that row, which means it should end up looking like that. Now, I shouldn't have to tell you how to make that happen, but we'll talk about it. But right, all I'm doing is making a new node, filling the data into that node, and inserting it into that, and starting, since it's the first node, I'm starting a new linked list with 31 is the only thing in there right now. Okay, I'm only writing 31. Of course, maybe you have maybe you have a name and some other things you're tracking. Well, those are all stored in that box too, along with the 31. But since 31 is the thing I'm using as my key, I'll just list those for brevity here. Okay, then maybe the next thing that comes in has a key value of 9. So I say, okay, let me hash that. So 9 mod 7 is 2. So 9 should end up in row 2 or slot 2. So okay, so I'll do that. All right, I'll go faster here. Maybe I'm going to insert a whole bunch of stuff. Just keep hitting next here. Great. All right, so maybe I insert some more things. Great. No big deal. Now, what happens when I have a collision? So first of all, if I try to now insert something with a key value of 2, 2 mod 7 is 2, because the remainder is 2 when you try to divide by 7. So that means this is going to try to go in slot 2, or the third row, I guess, as it's written up there, right? But slot 2. Well, this is officially now our first collision, or data collision occurs. Now, if we're using chaining, which you are going to be in your program for next week, chaining says, oh, all right, if there's already something there, then the new node that you want to insert is going to simply be prepended, as we've been using that term. In other words, inserted at the beginning of the list that's already there. So 2, which is what I'm trying to insert right now, since that belongs in slot 2, and there's already, a 9 there, I'm going to do a few lines of code in order to do this. All right, I'm going to prepend the list and say, let me put that 2, this new number 2. I'm going to put that, join that, I guess, right, or prepend that, so that now I have a 2 in the first box of that list and a 9 after it. And of course, I'll do one more here, 24. If I want to do 24, that has a remainder of 3. So that should go in row 3. So obviously, similarly, I would do something like this in order to move 24, this new number, prepend it into the list sticking out of slot 3. Okay, so visually at least, that's what we want to be able to do. Now, if we do this and we have something, we have a chart built up and this is nice and everything's organized, let's say I want to now find, that's certainly one of the things we want to be able to do is find things quickly. So if I want to find the 9, let's just for a minute here here, I'll take that down for a second. If I was just inserting these in a linked list, just if this was a month or more ago, and I was just doing a linked list with these nodes, I would have inserted all of those numbers, I think all of those, 42, 36, 2, 24, 46, 20. I would have inserted all of those, and then I would have done 9, and then I would have done 31, because I think that was the order that I put them, inserted them in. So 9, which is the number we're now going to look for, 9 would have probably, I think, would have been the 7th number inserted, which means if this was a regular linked list, I'd have to start at the beginning, and I would scroll, and I would say, is the first one the 9? Nope. Okay, go to the next one. Is the second one the 9? Nope. Go to the next one. Okay, and so on and so forth. And eventually, by the 7th round of that searching, I would find the 9. So I'd have to look for quite a while before I could find that 9 box. But now, with hash tables and with hashing, look at how quickly I'm going to be able to find the 9. So first thing I'm going to do is I'm going to hash the 9. So now this is me in the find or the search function or the search option from the menu. It says, oh, I want to look somebody up. So they entered a 9. So I say, okay, let me hash that. So I hash the 9, which gives me 2. Now 2 is going to tell me, oh, now, of course, I don't know if that 9 is in there or not. I mean, we do. We can see it. But but for sure, if there is a 9 to be had, it's going to be in that row. So if I'm going to now look for 9, I at the very least know I can start my searching right here. I don't have to look here and here and here and here and here. I don't have to look at any of those. At most, I'm simply going to read across this row on my quest to try to find the 9. So I can start with this first arrow, this first pointer, and I'm going to ask, is this the 9? So I checked 1, say, okay, well, no, it isn't, I guess. So I could say, oh, well, let me go to the next one. All right. And then I say, is this the 9? And I say, yes, yes, it is. So I only had to look at or it was the second box I looked at was the one I wanted. And in fact, in this particular example that we have in front of us, I'm never going to have to look at more than 2 boxes to find any of these, there's 8 numbers in this table. And I never have to look more than twice. Oh, that's pretty good. Remember, when we just do linear searching, or even if we do binary searching, we'd have to do log n for binary. We have to do log n. The log of 8 is 3. So this beats binary searching, and in fact beats it by a long shot, right? Because of course I'm going to be very, very much smarter about how I'm organizing my data in these hash tables. All right. Now, of course, if I was looking for a number that wasn't in the chart, so if I, let's say I was looking for the number 16. If I was looking for 16, 16 would also be in row 2 or slot 2. But of course, I would. If I said, okay, so is this 16? No. Go to the next one. Is this 16? No. Go to the next one. Oh, well, there wouldn't be a next one, right? So of course, obviously, as soon as I reach null, sticking out of the end here, I could say, oh, you know what? I checked everything in slot 2, and 16 would have been in slot 2 if it was there, but since it wasn't, or since I didn't find it, I can conclude very quickly that it isn't there. Oh my goodness, this is a huge time savings. I had to look at 2 numbers to know that a number wasn't in the list. So remember, of course, in regular searching, you have to look through the entire list before you're going to be able to conclude that the number isn't there. So, I mean, this is an enormous time savings over just sort of traditional lists, which hopefully makes sense. It should be. I'm being very much more careful and thoughtful of where I put stuff. So it should make sense that it's going to be way easier to find it later. All right. Okay, so that's the idea of a hash table. Obviously, there's the question of, so how do we code this, right? How do we get this off the ground? And obviously, you're going to be coding this in the next program that is posted on Canvas now. So you're welcome to start into that as soon as you want to. How are we going to do this? So as usual, we'll do a little bit together here, and then you'll take what we do and kind of run with it, hopefully. So I think we agreed that the structure that we want for a hash table is an array we know what an array is, but it's an array of linked lists. So in reality, what am I going to declare when I make my table, right, my hash table? What am I going to declare? I'm not going to declare a whole bunch of linked lists because that would be unnecessary, right? I don't actually want to say, oh, let me make 50 boxes, 50 nodes to hold data. We know that linked lists are very forgiving and flexible. So if I need space, I'll get it, or I'll ask for it. And if I'm done with some space, I'll delete it. So I don't need to necessarily get a whole bunch of space from the get-go, but I do need to develop a way for me to then be able to later on ask for space and have these linked lists grow and shrink as needed. So what should I declare when I'm declaring a hash table is I think I should declare something maybe like this, where I will say, well, let me make a table. Let me call the whole thing table, just because that hopefully kind of makes us think of that it's a 2D kind of a thing, rows and columns sort of thing. So I'll call it table. You call it whatever you want. If you don't want to call it table, you don't have to. Grid is also not a bad idea. So I'll call it table. But what is it actually? So first of all, it's an array. So we all, of course, remember, I know it's been a little while, but the brackets tell us, oh, hey, this is an array. Size is whatever the size of the array is, however many rows you want. So it's an array called table, but it's an array of what's? Oh, it's an array of pointers, that's what the star means, to nodes. So when we declare this thing, it isn't really a thing yet. I mean, it is, obviously it's a thing, but what am I actually getting when I do this? Is I'm going to get table. I'm going to do this small so I can squeeze it in. What am I going to get when I declare this table thing? Is I'm actually just going to get a bunch of pointers. Right? And this is slot 0, 1, 2, 3. Let's say size is 5. Then table bracket 0 is the name of the pointer sticking out of the first pointer, so to speak, in my table. Table bracket 1 is the name of the pointer that's pointing that will point to the list that's going to eventually be generated in the second row, and so on and so forth. Okay, so table. So if I do it this way, right? Table is the name of my array, but it's an array of pointers. I guess it's a little bit of a funny thing, right? I hesitate. I don't want to do boxes around these to make you think that they're nodes. They're not nodes. They are pointers who right now or probably when I get myself started, I probably want to say, well, right now they're all pointing to null because there's nothing there. Eventually, of course, we're going to probably put some boxes, some nodes over there so that I can actually store stuff. But at least from the get-go, they should probably all be assigned to null. All right, so table, so keep saying that to yourself, or if you're having concerns. Oh, I said it right here, second bullet. A good way to think about table, what is table? Table is simply consists of a bunch of first pointers. So it actually wouldn't have been the worst thing to call it first instead of table, but it sounds a little funny, so we'll stick with table. Right? But table bracket I, for any of those numbers, is the first pointer in each of the lists, in the list at row I, so to speak. All right? So this will take a little while to sort of get used to, but there it is. Maybe sort of keep staring at it, keep staring up here at this picture in the corner. So whenever I want to say start on a row, or, these are eventually going to be linked lists. So what do I usually do with a linked list is I have a first pointer, right? And the first pointer points to the first box. And that's how I sort of get on board, and then I, do whatever it is I'm going to do with it. So same thing here. It's just that each of these, so table bracket 0, that's a first pointer. Table bracket 1, that's a first pointer. Table bracket 2, that's okay, right? They're all first pointers. So if I need to do something on any given row, I'm going to start at table bracket whatever the row number is. That's going to be the name. That's going to be the equivalent of first in all of these linked list programs we've written. All right? So keep trying to tell yourself that. That seems to be where a lot of people get a little bit hung up on. So, okay, so with that in mind, so that's not much. I mean, that's me declaring the structure. So what else? Well, of course, we're going to hash these values. So, of course, I need a hash function. And again, most of the time, we're simply going to use as my hash function, I'm for the most part going to use just a mod, right? So I'm probably just going to end up doing something like, in most of these cases, return key, whatever the number is, mod, whatever size we're using for the array. So I'm mostly going to do that. So the hash function is going to, for the most part, I mean, we're not going to get too sophisticated. You could probably take a whole course in how to pick clever hash functions with prime numbers and all kinds of fancy math stuff, but we're not going to do that. We'll just say, well, I'm probably just going to do a remainder thing as my encryption, right, as my hashing. All right, so that's no big deal. So how do we get this started? So I'm going to hope that we have time for me to do a little coding, or for us to do a little coding, but let's do a little planning before we jump over to the editor. So, all right, so we've got this here. So this is sort of when we get ourselves going, that's kind of my initial picture, I guess, right, is I'm going to make the table. I'm going to probably set everybody to null. And now I'm going to say, okay, I'm ready. I want to start filling this thing. So how do we do that? So first of all, I have to decide. So I prompt the user, or if I have a file, I'm loading in from a file. But I get information about the thing I want to insert. I get the key value for the thing I want to insert. So of course, I think probably pretty much the first thing I'm going to do is I'm going to use the hash function to decide which slot should this new node be added to. Right? That's the whole idea of hashing, is that I'm going to first and foremost, I'm going to decide or compute where should this go. Great. Okay, so I do that. I'm going to get that number, probably stored in a variable, maybe a temporary variable, just to hold on to it so I can refer to it. And then what am I going to do? Well, all I'm going to do is the usual prepend code. You've written this several times already, so I hesitate to even mention it, but roughly speaking, I think those are the three steps, the 3 lines of code that we do each time, that we do prepend. So prepend, I think, is easier than append. Append meaning add it to the end. Prepend is easier because then you can just sort of make a new box and then stick that in, have that box point to the rest of the list. And that way it's up front, you don't have to do special cases or anything like that. Right? So these are just our usual 3 commands that we'll do in order to prepend. So that's hopefully doesn't seem too crazy. So, all right, so we'll write that code in a few minutes. But of course, as always, how do we know if it actually worked? Well, we'd like to probably be able to print the table in order to be able to see, does it look like this? Did I end up getting something that looks like that, right? Well, let's just stare at this for a second since we have it in front of us, or an example in front of us here. So what's, I don't have one that doesn't have stuff over there. There, okay. How do I print that? Well, I will say, obviously you don't have to worry about printing all the little lines and everything. That's obviously not important. But I do want to do some sort of printing where I can at least convey to the user of your program, me, okay, in row 0, there's a 42. And in row 1, there's a 36. And in row 2, there's a 2 followed by a 9, and so on and so forth. I want to print something at least that looks sort of like this. So I'll continue to let you stare at this for a minute while we think. Now, a regular linked list, that's no big deal. We know how to print a linked list. I take a pointer, I start it at first, I print and scroll until I reach null. Well, that might work pretty well if I'm trying to print, for example, that. Sure. But after I print that 9, I have to know that my next job is to print that. Oh. So, as it turns out, printing, which is almost always like the first thing we do, because it's like usually really easy, is actually not so easy for us here, right? In the sense that I have to be able to not only print across the rows, I also have to be able to print each row. right? Or in other words, I have to print each of those, I have to be able to print across and down, I guess is how I might say it. Now, we did this before, and we did it last semester, when we had a 2D array, like think about our maze games that we did, and in which case I used nested for loops in that case in order to say print I across the rows and j down the columns or something like that. Which I sort of want to do here. Now, this is an array, so I might use a for loop in order to say, let me scroll through the array. But then probably more typically, we use, or we might use, a while loop to print across each row. That's what we usually use to print a linked list. So we could do that, and I think actually in the shell program that you're going to use, I wrote a program that basically does what I just described here in arrows, even though that's not a full description of what to do, but basically use a for loop to go down, and then for each row, print across with a while loop. And that certainly works. But since we're still getting good with our lesson from last week, which was recursion, I'm going to say let's try to be a little bold here and do this recursively. Mostly because, again, we're building up our practice with recursion. So I think how to print this table, let's see if we can think about printing it recursively, which is going to be honest, it's going to be way easier, even though recursion is maybe something we're still getting a little bit familiar with. So let's try that. So I'll just, we're going to get some ideas together here, and then we'll bring them over to our program. So I'm just going to make a little fake list over here so we have one to look at as we're coding. So I'm not going to get too crazy here with size or anything. I'm just going to go with maybe, I don't know, maybe just 4, or I should say 5 rows, 0 through 4. And I'm just going to make some stuff up that might be stored in these various rows. So maybe I have a 10 here, and 5 here, and then null. Maybe there's nothing there. Maybe I got something here like 22, and then nothing. And I don't know, 13, 28. Okay, and then, I don't know, let's leave that null again. All right, so let's say I just made up some stuff here to fill our table. So, all right, so if I was going to print this, let's do the usual thing that we should hopefully all be doing when we sit down with a blank screen and we're like, well, how am I supposed to code this? So first we should describe as a human, how would I go about printing this table that I see over there? Well, I might say as a human, if I'm just trying to describe this to someone, who has no idea of how you would maybe go about this, I don't know. I might say something like, well, I would start at the first row, and I would print across that row until I got to the null. Oops. And when I reach the null of that row, I might come down to the next row. Something like that, right? And I would keep doing that until I got to the end. All right, so let me actually just do that in a color here. So on the one hand, I would start here. I'd start at the first pointer, and I might say, well, let me start at the first box, and I'll print and print and print until I reach null, in which case I'll say something like, go to the next row. Not quite sure how to do that yet, but we'll figure that out. And when I hit null, go to the next row and print. And when I hit null, go to the next row, print, print, go to the next row. And I have to do something in order to say, in this case, stop. Okay, so it's kind of, I don't know, right? I don't have a whole lot to say, I guess, about that, but I mean that is the general idea. I don't know, right? You have to sort of pretend that you're a printer, I guess, at this point, and say, well, how would you physically print these? Let's say you're trying to make you're trying to actually print this, on a poster or something. whatever shape you might end up with. I don't know. You'd probably start in the upper left corner and you'd say, well, I'm going to go across, and then when I get to the end of the one row, go to the next row. Print those across. When I get to that end of that row, go to the next row. And then when I get to the end of the last row is how I would know that I'm all done. Okay, so of course, yes, we could do this with some loops. And, I'd probably have a loop that's running through the rows. That's probably a for loop because my rows are an array. And then I'd probably have some while loops running across each row because those are linked lists. And I'd probably be able to do some sort of detection of when am I at the very end, hopefully. But like I said, we're going to be a little bit bold here and try to do this with recursion. So let's see if we can do this. I think this isn't actually that bad, but famous last words, I guess. So how are we gonna do this? So let's try this with recursion. So this will be our printing function. So I'll probably say void print. And I'm not quite sure what the parameters are going to be just yet because I'm not exactly sure what I need to keep track of, I guess. But I think we can probably be pretty sure I'm going to need to keep track of a temp, which is going to be where am I right now. So a good thing I'm trying to hopefully exhibit good behavior here for how you guys are supposed to figure out what the hell you're supposed to do. How many different behaviors do you notice me doing over here on the right when we went through this example? In other words, how many different cases, I guess is a good way to say it, or how many different situations might we be in? I'm going to count, but hopefully you can count this too. Sometimes, when I do this, I'm on a number, in which case I print the number and go to the next box. That's one case. So I might be on a number. What else might be true? I might be on a null. Now, if I'm on a null, I don't print. And I do something to say, go to the next row. So I might say, all right. Well, recursion, even if this was a loop, but especially with recursion, we should always be trying to think about how many different behaviors or situations might I be in. And so far, I might say, well, it feels like I have two cases or two situations. Either I'm on a number or I'm on a null. And my behavior is different depending on which of those two cases I'm in. Well, those are probably both cases for my recursion over here. And so maybe two cases is enough. So I won't write this down just yet, but maybe I'll have one case for what if you're on null and one case for what if you're not, or you're on a number. But now I would ask, and if we were in class, I would stare at you until you gave me the right answer. Is two cases enough? So in other words, am I able to describe, well, if you're on a null, do this stuff. If you're not on a null, do this stuff. And here's where I would stare at you and say, no, that isn't enough to just say, if you're on a null, if you're not on a null, And I would ask someone to point out for me why there's actually three cases and not just two. Now, the two that we said, yes, those are both there. But what's the what's the third case of where I need to maybe be even more, or where I have a different behavior? Well, a minute ago, I sort of glossed right through this. I said, if you're on a number, print it and go to the next box. Well, that sounds pretty accurate, right? Every time I'm on a number, I print it and go to the next box. So that's all right. But if I'm on a null, it matters whether I'm on this null or this null. Why? Because this null says, don't print, but go to the next row and keep going. So in fact, 1, 2, 3, 4, these four nulls all act the same way. All four of these say, don't do any printing, but do keep going. However, this null is a null of a different type. This is the null where I say, stop. Now that's a different behavior than the other, in this case, four nulls. So I make a big deal of this, because of course, usually when we write a recursive function, it's usually most helpful to first try to talk about, how do I know when I'm supposed to stop? So I think, if you believe what I just said, I will stop only when I'm on null and I'm on the last row. So if I'm trying to keep track of things, so I'm saying all of this to say, how does he always know how to get these things started? Well, you just, again, I think you're mostly just trying to think about when are you, what are your behaviors? How are your behaviors different in one case versus another? This also helps us to identify what do I need to keep track of. Remember, the parameters of a recursive function are basically all the things you want to keep track of for each round. So I know I need to keep track of a pointer for, where am I in my thing. But I might also need to keep track of which row am I on, because it matters whether I'm on row 4's null versus row 1, 2, 3's null. I will behave slightly differently. And since this is something I need to be able to detect with recursion, anything you want to be able to detect or keep track of, you probably need to make a parameter. So I'm going to also make a parameter called just row or something like that. So that way it'll tell me which row, I can keep track of which row are we on. All right, maybe I need something else, but if I need something else, I'll add that in a minute. All right, so far so good. So plan-wise, I feel like 3 cases might do this. So let's go. So the first case, which is always easiest to say, is when do I know that I'm done? So I could certainly say if temp is null, so you're at null, and you're on the last row. So probably you have some variable that's keeping track of size. So in our example, of course, since I have 5 rows and 5 rows, size is 5. So here I might say if temp equals null and row equals, I suppose I should say size minus 1, right? Because that would indicate perhaps that we're on the last row. I could say it's something like that, right? To be honest, even if I went to the next row, I'd probably, maybe not. Okay, well, let's say that, right? Because that exactly describes our picture here. I'm on the null, and I'm on the last row. Oh, here's where I want to say, all finished. And don't do anything else, right? So, of course, for recursion, I think about my base case is the one time where I don't call the function again because I'm actually done. So I'll print a cute I'm all finished message, but most importantly, I will not call the function and say keep going. Okay. All right. So that's one case down. So that'll handle this one. All right, what else? So we have 2 other cases. One is that I'm on the end of a row and I want to keep going. And the other is that I'm on a number and I want to keep going. Now, it a little bit matters which order you do these in, because of course, if I'm on null, if temp is on a null right now, I can't really ask about temp's num. So it probably doesn't really matter which order we do them in, but I'll handle the nulls first maybe. So, all right, so else if you are on a null, so if we are at the end of a row, now I don't have to say and row is not size minus 1, because of course if this was true, I will not do the second case. So this is really automatically saying if temp is null and you're not at the last row, then what do I want to do? Now, of course, those are my green arrows, my green go down to the next row arrows, right? So now I just need to ask myself, well, what do I need to update in order to simulate go to the next row? Well, an easy thing that I obviously need to update is I probably need to say row plus plus, because if I was on row 0, I probably now need to say I'm going to be on row 1. Okay, that's an easy thing to update, I think. All right, let's see, who else needs to be updated now? Okay, so if I was on row, I'll just use this one. If I was on row 0, row is now updated to be the number 1. But my pointer, temp, is still on this null. But I think in order to get it ready for the next round, I would want to advance it to the first pointer of my new row. In other words, actually do this arrow that these little squiggle arrows that I've been outlining. Do it. Oh, So how do I say that? Well, so numerically row has been updated, but temp hasn't been moved. But let me move it now. So row is now the number row here is the correct new row. So if I want to move temp to be the first pointer in that row, this is where I say a table. Temp equals table row. That always looks a little funny when you first look at it, right? Because it's well, I don't know, right? It just always does. But remember, table, bracket, 0, bracket 1, bracket 2, bracket 3, bracket 4. Table, bracket, 0, 1, 2, 3, 4 are these first arrows. So if I want to move, let's say that row was 0, and now I'm going to, and temp is here. If row is 0, this makes row equal to 1. And now I want to say, and the new value of temp is table bracket 1, which is this first arrow. So now when I come back up to the top, it's going to, I'll say, okay, now what? Now what? All right, so I updated my two parameters. So remember, it's usually a good idea to just double check. The parameters for your function, at least one of them at least, probably needs an update each time. In this case, I updated both of them. And so now I think I'm ready to say, and call the function again. I'll say, okay, now print, and I updated temp. That'll have been advanced to the next row, and I updated row to be one more than it used to be. So I think that'll work. I think that'll work to get me off of the one end of one row and onto the beginning of the next one. Okay, so that's maybe case 2, and then case 3, which we can just do with an else here, I think. Otherwise, I'm on a number. So the usual thing I would say, of course, obviously I want to print the number. And who is this? So temp. I'm still using temp, right? So let's not overthink this. So temp is still my scroller. So temp, see out temp's num. I want to probably advance temp. So sorry if you let me, I'm just going to illegally squeeze another line in over here. So I want to print what's in temp. So the 10, let's say. I want to probably scroll temp to the next box. So temp is maybe over here at 5 now. And I'm ready to call the function again. Now, of course, I didn't update row, but that also makes sense because I wasn't ready to go to the next row yet. But I did update temp. So now when I call the function again, I will at least be sending it a new location for temp, but I'm going to send it the same number for row. Okay, so what do I got here? I guess I have 6 lines of code. I mean, I've got some ifs and elses as well. But I think this is actually somewhat shorter to do it with recursion. I know we're maybe still kind of getting happy and comfortable with recursion, but anytime you have these sort of processes where this is kind of where you end up, where you're saying, well, what am I doing here, right? What am I printing? Okay. But how is my behavior different? I think that's usually a good way to sort of try to identify. In this case, there's 3 cases. These 2 are both recursive, case 2 and case 3, because I call the function again. And this is my base case, the if, because that's where I don't call the function again. Now this is a void function, so I don't have to worry about returns, because I don't have any returns. So I'm okay. If this was a return function, if I had a int or whatever I was sending back, I'd probably want to put returns in front of every function call. All right, so this works, right? And I think we're short on time, so I will wrap this baby up. But if we take this and plop it into an editor, as long as we didn't mess it up anywhere, we'll do a little other formatting. So if you want, you can sort of be a little craftier about saying, oh, how do I get the 0, 1, 2, 3? So we could do that too, right, if we're dying to. But at the very least, and I also don't have end lines, so I actually probably was a little sloppy here. This is going to work, but it'll print it all together because I put absolutely no end lines in here. So I probably do need to go back and just throw another line or 2 in here, but that's okay. But we'll clean this up when we import it into our editor. So we'll do the printing function together next time, and this guy, right? Obviously, we want to actually be able to put stuff in there so that we can, when we print, it's actually printing something. So we'll do both of these next time and get a nice little shell or starter program together so that you can have a good starting point when you do the usual business at this point, which is to take the few operations that we code together and expand upon that to add our usual things like deleting and searching, and I don't think we did a find largest on this one, but other sorts of things like that. So you're welcome to start into the program if you're feeling ambitious, I guess, or anxious about getting started. If you want to wait until after the last video for this week, where we'll have a little more coding practice together, that's probably not a bad idea.